Yes. Okay, hi everyone. Any questions before we start? Nope. Okay, so for this first problem, we're going to show, we're going to derive De Morgan's law using these two facts. So I'll give you a minute or two to figure out how to do this one. So remember that, for example, if we have a rule with A intersect B, we do A dot B, A union B goes to A plus B, A complement goes to A tick. The universal set is 1, and the empty set is 0. So do other people have this done? Okay. Does anyone know how to get started? I'll give you a hint. So you can do this. So we can use the distributive rule here to rewrite this as A union, oops, nope, A times B plus A prime. Am I doing this back? I am doing this wrong, sorry. We can't distribute over that. Okay, yeah. So the way I did this earlier is I used the associative rule to rewrite this as this. And then by the commutative rule, we can write this as this. Nope. And it's so one way to know what you're kind of looking for is we want to show that this is 1. So we want to, maybe show that we have a union between something and its complement, which will give us a 1. So that's why I'm deciding to do this. And so this is, so I'm going to use the distributive rule underlined for this one. And we get A complement plus A times A complement plus B prime. And this is distributive. So this right here, we can apply the negation rule, and we get 1 times A prime plus B prime. And then next, we would like to use the identity rule right here. So we're going to need to do an application of the commutative rule first to do that. So we get A prime plus B times 1. And that's commutative. And then finally, we can apply negation or identity to get A plus B prime, or A prime plus B prime, and that's by identity. Oh man. And so we can now use the associative property to rewrite this as A prime plus B prime. And now we would like to apply the negation rule again. So we would do A prime plus 1 by negation. And finally, we have something that's like A union the universal set. So we now can apply universal bound to get 1. Everyone with that? Yep, okay. And for the second one, for this one, I started by doing the distributive rule. So maybe I'll give you a minute to do that.
But there was a question about the previous one.
Oh, okay. I missed the application of commutative, sorry. Where did I, yeah. So I should have had a commutative application to do A plus. I'd have lost a point there. We're not going to take off for that again, so, but yeah. Good question. Only commutative, that's the only one you can miss. I'm going to just start writing what I told you I was going to do. Doing this one. So I'll give you a hint. From here, we only need, we're going to be doing some applications of the associative rule and looking to apply negation and the commutative rule. Anyone done? I'm going to say no. So maybe I'll do part of this and then someone can show me, can help me do the other half. So I'm going to use the associative rule here. So I'm going to get A times B prime. That's by the associative property. And then if we look, we can use negation. So we have an intersection. So we get A times B times A prime plus A times 0. This is by negation. And then we can use, what's the name of it? Universal bound again, to get this to be A times B times A prime plus 0. And identity will give us that this is A times B times A prime. So doing this part is very similar to that. So does anyone want to take a stab at doing that? No? Okay. So first I'm going to apply the commutative rule to get A prime out in front. I'm going to get A prime times A times B. I don't need the outer parentheses now, but and so now I'm going to reassociate to get A prime times A times B. That's the associative. And then this is equal to A times A prime times B. That's commutative. Can we do commutative to swap A dot B to B dot A and then use associative on the second one? Oh, yeah. Actually, that's probably a better way to do it. That way we don't have to do commutative twice. Does anyone want to see the less dumb way? Oh, man. What did I do? Okay. Oh, man. Okay. We'll do the less dumb way. So what Brendan recommended was that we apply the commutative rule on this first. So we get B times A prime. And then we can do a reassociation to get B times A prime. And then we can do negation. And this is equal to B times 0. And then because we were smart about how we applied the commutative rule, we can now do universal bound, yes. Universal bound to show this is 0. Any questions on that? Can we do the same alternation to the 2 part in the same step because they have similar structure? So I recommend that you do these one step at a time in case you make a mistake. However, if you are doing 2 pieces at once, that should be fine. Just if you make a mistake, it decreases your chance for extra credit or partial credit. So any more questions? Okay, move along. So for this one, we're going to do the arrow diagram between the power set of this set and this set. And then we're going to draw arrows according to this relation. So to get you started, we need to draw the members of the set. I'm going to draw them a little funny with space because I ran out of space last night doing this. So we have all the members of the power set that have 1 element. So I recommend you try to be very systematic about how you write down the elements of the power set. And then for the 2 element ones, we have 1, 2, 2, 2, 4. I'm not being systematic. 1, 4, 1, 8. And then we already did 2, 4, so we need to do 2, 8. And then 4, 8. And if, so when you're doing power sets of 4 elements, you should have 6 elements with 2 elements. 6 sets with 2 elements in them. So 1, 2, 3, 4, 5, 6. And this comes from the binomial theorem. Yes. For 3 sets, we should have 4 because we're basically leaving one element out. So for the 3 sets, we have 1, 2, 4, so leaving 8 out. 1, 2, 8, leaving 4 out. 1, 4, 8, leaving 2 out, and 2, 4, 8, leaving 1 out, and then the full set. So 1, 2, 4, 8. Then we have 0, 1, 2, 3, 3, 4, 5, 6, 7, 8, 10, 11. Okay, so does anyone want to tell me where the empty set maps under this relation? So the relation says that we map to the number n in B if the sum of the elements of that set is equal to the number in B. So what about this first one? The set with just 1 in it?
Map to 1.
Yeah, exactly. What about 1, 2, 4, 8?
The 15.
Yep. Yep, 15. So I'm asking about this empty set here. What do you think the sum of the elements in that is?
0.
Yep, exactly. So does anyone have a guess at what this whole thing is going to look like? So I'll give you a hint. So if we had binary digits, B3, B2, B2, B1, and B0, then, so we have a 4-bit integer here. It's going to count up from 0 to 15. So basically what we've done is we've written all sets that have ones in these. Does that make sense? Messy? Yes, it is messy. I need to mute this. Oh, yes. It is going to end up very messy. Yeah, so you're going to have all these arrows going all over the place. But basically what you're going to have is you're going to have one arrow going to one of these. So it's going to be 1 to 1 and on 2. Shut up. Any questions on that?
This is kind of just like binary numbers, right? We're like
Exactly. So basically what we're saying is a 4-bit number, you can count up 0 to 15 uniquely. Yep. Okay, so not seeing anything in chat. So this is one of those fun ones where we, again, have a power set. So we're going to actually have 3 sets here. So we're going to be doing a composition. So before we get started, just looking at these, do you think that C of n is defined or n of C is defined? So remember, you applied the one on the right first. So one of these doesn't make sense to do. So basically we have C goes from P, the power set of X, Y, Z, to the power set, X, Y, Z. And we have N, which takes elements from power set of X, Y, Z to N, to these numbers here. So if we tried to do C of N, what that's saying is, so we take the C of N of X, this is equal to C of N of X. If we look here, this is going to give us something like 0, 0, 1, 2, 3. C can only handle elements of the power set. So the only one that makes any sense is N of C. So any questions on that? So we're going to have 2 copies of the power set. Yeah, so C takes elements from a set to the same set. So if we look at the definition of C, we're basically subtracting the argument from the whole set. So basically what the C relation is doing is relating the elements of the power set to their complement in the set. So we should have 8 total elements written here for our power set. And if you remember your binomial theorem, we should have 3 of 1 element, 3 with 2 elements. So it's good to check to make sure you have the expected number of elements. And in the interest of time, I'm going to copy and paste this. Oops. That better work. Oh. There we go. Apparently PowerPoint is not very stable. And then we're going to have 0, 1, 2, 3. So yeah. Does anyone know where the empty set goes?
0.
Not quite.
XYZ.
Yeah, so XYZ. So remember that the C relation subtracts King writes that C of n is not defined, so we need to do n of C. So we have XYZ, the whole set minus A. So minus the empty set, we get the full set. Likewise, if we do XYZ, where does this one go? So XYZ minus XYZ is the empty set. Just maybe do 2 more of these. Basically, what you're looking for is the complement. So XY is going to go to Z, XZ is going to go to Y, YZ is going to go to X. So you're going to get this really messy intersection right here, the way I've drawn it. Finally, we need to do the arrow diagram for the composition. One second. Make sure I'm doing this. Yep. Okay. So 0 goes to, so the empty set goes to 0. These ones go to 1. That doesn't go to 2. So the n relation is the number of elements in the set. This one goes to 3. And so this is our compressed diagram, our expanded diagram. And then the question asked us to draw the arrow diagram for the composition. So no, I'm doing this wrong. We need to do one for this set and just do where it maps in the other domain, in the ultimate domain. So if we think about what the definition of these functions is, C took each element to its complement, and N takes the set to the number of elements in the set. So, so N of a set, what's the best way to say this? So 0, the set with no elements in it, doesn't subtract anything out of X, Y, Z. So this one goes to 3, right? Each one of these is going to take 1 element out of X, Y, Z, leaving 2 elements, so they all go to 2. Each of these take out 2 elements, so these all go to 1. So it measures the number of elements that aren't in the set, yes. So one way we can interpret this result is that if we take n of s, so say that n of s that k equals n of s, and let's say that big N is the number of elements in the set. Then n of s complement is equal to n minus k. So that's kind of what this relation is saying. Does that make sense? Yes. Savine. Did I get it right?
It's Savine.
Savine.
Savine, yeah.
It's closer than 7.
Yeah. So sorry, my question was like earlier in the beginning of the problem. So can you explain again why C of n is not defined and n of C is defined?
Okay, yeah. So if we look at what n does, so n takes elements of the power set. I'm just going to write it abbreviated here, to 0 to 3, right?
Yeah.
So if we apply n first, we're going to put, so let's say we do n of a, then this is going to be, say, 0, right? For example.
A, like lowercase a.
Okay, let's just n of x. So just some argument to it. Maybe let's not do, let's just do an actual one. So x, the set of x, okay? And this goes to 1, right? C works on the power set, right?
Yeah.
So so does x, y, z minus 1 make sense? And so this isn't part of this, right? And it's not a set. Does that make sense?
So XYZ minus 1 is saying elements in XYZ, but not in 1.
Right, so we're doing set difference. So that's what C is doing, it's a set difference operation.
Oh, so 1 is not a set. So
1 isn't a set, and it's also doesn't have anything to do with the sets that C talks about, right?
Oh, okay.
Does that make sense? Yeah, so the output of n is not compatible with C. So it's kind of like, a function that takes an integer and then giving it some structure or something, right?
Oh, yeah.
Yeah, that's a good question.
Thank you.
Many other questions on that? Where am I? Yeah, so we're getting so someone says it would just be the amount of elements that are missing from XYZ. Yep, that's right. What do we write for the function names? Do we just write C of X and N of X above the arrow lines? Sure. Yeah, that's fine. Yeah, this one's fun. So we're going to do an arrow diagram on this one, where the rule is that the difference between two elements, if there's an arrow if there's a difference between two elements. And if I could count right, yeah, so so can someone tell me one arrow that's in this relation? So we're looking for ones that have a difference of 3. Yep. So Kevin says there's an arrow from 6 to 3. And Brendan says there's an arrow from 3 to 0. Is there an arrow from 3 to 6? Yeah, there's an arrow from 0 to 6. Are these two-way arrows? Yes. So, 3 minus 0 is 3. 0 minus 3 is negative 3. They're both divisible by 3. And the fact that the other becomes negative doesn't affect divisibility by 3. So all of these are double arrows. Yep. I'm seeing 1 and 4, and 5 and 2. So 5 minus 2 is 3. 2 minus 5 is negative 3. Ah, yes. And then Kevin mentioned the one that's really sneaky. So 0 minus 0 is divisible by 3. 1 minus 1 is divisible. So these are all 0 when you subtract. Okay, so yeah, so this one's easy to forget. So when you're doing this, remember that that the relation is working on this set. So we need to consider all pairs, including things like 0, 0. Yep. So 0, yeah, we already have 0 and 3. Let me delete this. So now we're asking about the relation R of R. And so if we remember our definition, it says that there exists an X in A. So if we say that A R of R B, then there's some X such that A is related to X and X is related to B, right? So I'll give you a minute to think about what R of R looks like. How many more problems do we have? So I'll give you a hint. So the definition of the relation is that there exists some integer k such that we can write this, and x minus b equals 3l for some integer l. So what I'm trying to get to is I'm trying to show that that this means that A relates to B. So basically, I'm trying to show that R of R is inside the, is a subset of the R relation. So what if we add these two together? So if we add them together, the x's cancel here. We get A minus B is equal to 3 times k minus L. So this means that 3 divides A minus B, right? So this means that AB is in the original relation. And we can see that actually in this diagram, because anytime, so take for example 3 and 0. We go from 3, we could say, oh, well, 6 is an element in between, right? So we can go 3, 6, 0, but 3 and 0 is there. So that's what this is actually saying, is that this relation, this composed relation, is actually the same as the original relation. And it's because of this property that no matter where you can get to it by a shorter, so, you know, if I can go from here to here and here to here, I can get to it this way. That's what this is saying. And then to complete the proof, we need to show that if A is related to B, then A R of RB. And you know, so we can basically just say that if we look back here, all elements are related to themselves. So I can say A R of R A and A R B, but this is the definition of this. Does that make sense? So this shows that did I go too fast on that?
Just
I have a
little-
feeling, huh?
Just a little fast.
Okay, yeah, okay, that's fine. So what I'm trying to get is that, so as a general concept, I'm trying to look for x, y. X was related to y, and y is related to z. And this is this shows that x is in this relation, right? By our definition. So if I'm trying to show that A and B are in the composed relation from here, I need to come up with some sort of intermediary element right here, right? So I have right here A, so I say R, A, R, Y, and we're still looking for this element here. Does this make sense?
Yeah.
Okay. And then I just said, oh, well, my slides are really messed up. I said, oh, well, look at this. All of these all have an arrow pointing back to themselves. So we know that every element is related to itself. Yep. So I can say, oh, well, I can put A here and A here, and that will show that it's here, right? So this shows that along with the last slide, and this shows, the last slide showed that the composed relation was a subset of the main relation. So we've just shown that the two relations are the same. Is that good?
But how can every number relate to itself if every other number isn't divisible by 3?
Okay, yeah. So, so we have a number A, and the definition of the relation is that its difference is divisible by 3, right? So we're looking for this, right? So A minus A is equal to 0, right? And this is divisible by 3. So every number is related to itself under this relation. Good question. Anything else on that? I probably won't put something very hard on the quiz with these. Not going to make any promises because I haven't written it yet, but and the final part of this asked what the meaning of this relationship is in English. And so basically, if we have so this is the same notation that I'm using over here, not there. So if this is the same as saying that x r of r y, using the same thing. So this means that there exists a z such that what did we name our set? A, yeah. So there's a z and a such that x is related to z and z is related to y, which means that x minus z, which means that 3 divides x minus z and 3 divides z minus y. So I think that's probably about as far as we're going to make it today. I think this lecture was a little too long. Any questions on that? Is this topic confusing?
If I could speak for myself, I was very confused at this entire lecture.
Okay, yeah.
I was
think-
maybe confused on the last problem.
Yeah, so if you work through it, you should, so I would recommend you work through these some more. Relations are kind of strange. I mean, it's possible I didn't present the last one as well as I could have. I mean, so if another thing you can do is you can go look at, so we put all our lectures on YouTube, so you can go look and see how other instructors do it. And maybe that will be helpful. So any other questions? If not, oh. So I don't know how to prove R equals R of R in detail. Okay. So if you want to show two sets are the same, you can either do an element-wise proof or show this. So you can show that they're both set, you show that they're subsets of each other, right? Actually, I guess I am doing an element-wise proof. So for this one, let's assume that we have A, B is in R, right? So what we need to find to show this one is that there exists an X in A such that AX is in R and XB is in R. And I said, oh, well, A is an A, and we know because of the self arrows that A is in R. So we can say AB is in R, and that's from here. So then that means that AB is in R of R. Does that make sense? And then for the other way, we say that AB is in the R of R relation. And by the definition of the composition relation, that means that there exists an X in A such that A is related to X and X is related to B. And this means from the definition of a relation here, no, not here, here. So if X minus Y is divisible by 3. So this means that A minus X is equal to 3K for some integer K. And this one here means X minus B is equal to 3L for some L and K in Z. And then I added these two things together. So I did A minus X equals 3K plus X minus B equals 3L. And so this cancels out with this, and we get A minus B equals 3 times K minus L. By closure, this is an integer. And this means that 3 divides A minus B, so we have A is in the original relation, and that shows this. So we showed equality between the two. Does that help? Okay, good. If there's no further questions, I'll post this on the, hopefully cleaned up a little on the Canvas. Thank you, everyone. Oh, need to do stop YouTube.